Okay. Hello, everyone. I have decided to do two videos for two examples from section 3.5. And I'm doing this because I actually, when we went over this in our notes, and in particular example 3, so all of the other examples are fine, but in example 3, I assumed something that I couldn't assume to solve the first part, and I wanted to go back over it because it's important that you understand the correct way in approaching this problem so you'll know how to approach future problems. So I'm going to go back over this example and then I'm going to do one similar to something that you have on your homework in that section. And so the homework will now be due Friday, and I just wanted to go over that. So again, remember in example 3, we either had to use our exponential growth model or decay model. And like I said, for the most part, you will be given the model in the problem, except unless it's a decay or a growth, because that one, for the most part, they expect you to memorize because you have to derive different variables in that function. So I just want to quickly recall when we talked about this, we talked about the different variables. And so in example 3, anytime we're talking about the half-life of something, that represents decay. So we're going to use our decay model, which is right here. And so in terms of the variables, A represents the initial amount or size of a growing or decaying substance. B is a constant to represent the rate of growth or decay. X represents the number of years of growth or decay. And Y is the amount or size of a substance after a time of growth and decay of the amount A. Okay. And so in part A, you are asked to write an equation for the amount of radioactive present anytime T following the accident. And so just kind of recall, this problem talked about a byproduct of radioactive iodine where the half-life is about 60 days, which means after 60 days, a given amount of radioactive iodine will have decayed to half the original amount. And I'm underlining that because that's something I sort of skipped over, but is really important in setting up how we're going to solve this. And so it says, suppose a contained nuclear accident occurs and gives off an initial amount of C of radioactive iodine. Okay, so we know we're going to use the decay model, and we can replace, since we're talking equation in A, they want us to talk in terms of time T and our initial amount C. We're going to rewrite the decay X function as Y equals C times E to the negative BT. Okay, and so the other information we're given, let's look at it as the point. X and Y are actually, since we're doing, I'm going to go back. We're going to actually use, since it's in terms of T and Y, let's do T for time and Y. Okay, and remember again, so T represents our time and Y represents the amount or size of a decay after a time of growth or decay of a certain amount. I just wanted to go back to show you that. So what they gave us is that 60 days, so at time T equals 60, it's a given amount will have decayed a half of the original amount, and so, or the initial amount. And to represent that, then T will be represented with 60. Y is going to be represented by 1/2 times C, because it's 1/2 the original amount, and that's what I omitted, which is very, very important. And so I wanted to go back over this to make sure you understood exactly what's going on. So Y is 1/2 of your original amount. Therefore, when we do our equation, so we have to solve for B, basically. That's what we're solving for. It would be Y, which is 1/2 C, equals C times E to the negative 60 T. I'm sorry, negative 60B. Because T is 60. Okay. And so the C's go away. So I assumed that it was 1, but we can't assume that. But they go away anyway. So we'll have 1/2 equals e to the negative 60b. Now I'm going to continue on this next page. So 1/2 e, I'm sorry, let me go back. 1/2, yes, equals e to the negative 60b. And now remember, so we have that variable trapped up in the exponent, so we want to take the natural log of both sides. And since 1/2 is exactly 0.5, you can actually use 0.5 instead if you want to work with decimals. And so we'll have natural log of 0.5 equals negative 60b, and then those are inverses of each other, so that just becomes a 1. And then we divide both sides by negative 60. And so when you approximate that, and I'll have it on exam or a quiz to round off to about 3 decimal places. So B is about point 0.012. And so then for A, the answer is y equals C times e to the negative 0.012t. Okay, so I'm going to stop this video here and go on to the next one to solve part B, which is actually the same as what we been doing, but I'm going to do it again just to make sure you guys are clear.